All right, let's talk about electric circuits. We're going to go on a little journey, starting with some fundamental laws of electricity and ending up with the actual tools you'd use in a lab. You're going to see how just a couple of simple rules can help us crack even the most complex electrical puzzles. So, you probably know Ohm's law, right? V equals IR. It's great, it's perfect for a simple circuit, one battery, one resistor, nice and clean. But what happens when things get messy? When you've got multiple power sources, all these different loops, and resistors just scattered everywhere? All of a sudden, that simple little formula, well, it just doesn't cut it anymore. I mean, just look at this thing. You've got two different batteries pushing current around. You've got these junctions where the path splits and then comes back together. Trying to use only V equals IR here would be an absolute nightmare. We need a better system, something more powerful. So what's the game plan? First, we'll see exactly why we need to move past Ohm's law. Then we'll get into Kirchhoff's two amazing rules that give us a new foundation. After that, we'll see these rules in action with some really clever devices like the Wheatstone bridge and the potentiometer. And to wrap it all up, we'll see how these ideas let you build the very meters you find on a lab bench. Yep, to handle a circuit as tangled as the one we just saw, we need something much more robust. We need a set of rules that works for any circuit, no matter how complicated it looks. And those rules came to us all the way back in 1842 from a guy named Gustav Kirchhoff. He laid out two simple but unbelievably powerful laws that are the bedrock of circuit analysis. Think of them as the official rules of the road for electricity. Okay, the first law is called the junction law, and it basically says that at any point where wires meet up, what we call a junction, the total amount of current flowing in has to equal the total amount of current flowing out. It's all about the conservation of charge, You can't just create or destroy electric charge at an intersection. So let's look at this junction right here, at point P. You can see you've got a few currents flowing in, I1, I3, and I5. And you've got a couple flowing out, I2 and I4. The junction law is super simple. What goes in must come out. So I1 plus I3 plus I5 has to be exactly equal to I2 plus I4. The easiest way to think about this is with plumbing. Imagine a bunch of water pipes all meeting at one connection. The total amount of water you're pumping in has to be the same as the total amount of water coming out through the other pipes, right? The water doesn't just vanish. It's the exact same idea for electric current. So Kirchhoff's second law is the loop law. This one says that if you trace any closed path, any loop in a circuit, all the voltage gains you get from batteries and all the voltage drops you get across resistors, they all have to cancel each other out and add up to zero. This one is all about the conservation of energy. Here's a great analogy for this one. Imagine you're out hiking on a trail that's a complete loop. You might go up some steep hills and then down into some deep valleys, but when you get back to your car, you're at the exact same elevation you started at. Your net change in height is zero. Voltage in a closed circuit loop works the exact same way. Okay, so we've got these two powerful laws, but what are they good for? Let's see them in action. The first tool we'll look at is the Wheatstone bridge. It's a really clever invention for measuring an unknown resistance with just incredible precision. So here's the classic setup. It looks kind of like a diamond, right? With 4 resistors. Then you've got a power source connected across the top and bottom. And right there, smack in the middle, is a galvanometer, which is just a super sensitive device that can detect even the tiniest bit of current. Now, here's the magic trick. The whole point of the Wheatstone bridge is to adjust the known resistors until that galvanometer in the middle reads exactly 0. No current flowing through it at all. When you hit that point, the bridge is officially balanced. So, how does that help? Well, if there's no current flowing through that middle path, it can only mean one thing. The voltage at point B is exactly the same as the voltage at point D. And when those 2 points are at the same potential, something beautiful happens. The math gets super clean, and you're left with this simple, elegant ratio. If you know 3 of the resistors, you can now calculate the 4th one with amazing accuracy. Building on that same idea of finding a null point, or a zero measurement, we get another incredibly precise instrument, the potentiometer. If the Wheatstone bridge is like a precision scale for resistance, then the potentiometer is like a precision ruler for voltage. Its principle is just so elegant. It uses a long, perfectly uniform wire. And when you have a steady current flowing through it, the voltage drop along any piece of that wire is directly proportional to its length. It's literally a ruler. You want half the voltage? You just go to the halfway point of the wire. It's that simple. Now, you might be wondering, why not just use a normal voltmeter? Good question. The difference is actually critical. A standard voltmeter has to pull a tiny bit of current out of the circuit to work, and by doing that, it slightly changes the very voltage it's trying to measure. The potentiometer, on the other hand, using that same null deflection method, draws zero current when it's balanced. That means it measures the true, undisturbed voltage of a source, making it way more accurate.
All right, time for the final piece of the puzzle. We've been talking a lot about this sensitive little detector, the galvanometer. Well, it turns out that this one core component is actually the heart of the everyday meters you find in any lab.
This is it, the moving coil galvanometer. A current goes through the coil, that creates a magnetic field, which interacts with the magnet, and that makes the pointer move. It's amazing for detecting tiny currents, but that's also its weakness. It's incredibly delicate. So, what if you need to measure a really big current? You can't just send it all through this fragile coil. You'd fry it. The solution is brilliantly simple. You just add a low-resistance detour, a shunt, in parallel with the galvanometer. This shunt acts like a bypass, letting most of the current flow around the sensitive meter. And just like that, you've turned a detector into a tough, useful ammeter. And what about measuring a huge voltage? The logic is just flipped. To turn our galvanometer into a voltmeter, we add a really high resistance resistor, a multiplier, in series with it. As you can see, this giant resistor basically soaks up almost all the voltage, letting only a tiny safe trickle get to the meter. And there you have it, you've built a voltmeter. Isn't that cool? So, let's bring it all home. We've gone from these abstract physical laws all the way to designing the actual tools we use to measure and work with them. So, what are the big takeaways here? First, Kirchhoff's two laws are the universal rules for any electrical network, period. Second, that clever null point method is the secret sauce for getting insanely precise measurements without messing up your circuit. And finally, those common meters we use all the time, they're really just a sensitive galvanometer wearing a clever disguise.
It's really amazing when you think about it. Just two fundamental ideas about conservation give us this entire toolkit to measure, understand, and build our electronic world. So the only question left is, now that you know the rules, what will you build? What will you discover next?